Silicone wafers are the basis for modern microelectronics. For computers, mobile phones, the internet, DVD players, flat-screen monitors, navigation systems, airbags, computer tomographs, and aircraft controls, to name but a few. Their production requires the highest standards of precision and purity. Siltronic uses two crystallization processes to produce silicone ingots: float zone pulling and Czochralski pulling. Polysilicone in the shape of a rod is the base material for float zone pulling. The polycrystalline silicone rod is suspended in the pulling system and the seed crystal mounted vertically. The seed crystal determines the orientation of the later monocrystal. The raw material is heated by a high-frequency coil and brought into contact with the seed crystal. By slowly lowering the rod, the melting zone gradually moves from bottom to top. The lower part of the crystal solidifies according to the orientation of the seed crystal. The process illustrated here has been speeded up. In reality, it takes between 10 and 15 hours. Removal of the finished ingot requires utmost attention from our operators. Mistakes that are made here may cause irreparable damage. The operator then lifts the monocrystalline ingot out of the pulling system and is transported away for further processing. In Czochralski pulling, a silica crucible is filled with polysilicone. As in all further steps, absolute cleanness is crucial here. The seed crystal is installed suspended in this process. Here too, the seed crystal determines the orientation of the finished silicone ingot. The electrical heating melts the polysilicone in the crucible while it is rotated. The melting point is approximately 1,420 degrees Celsius. The seed crystal is dipped into the melt and slowly pulled out again. Through the slow pulling process, the melted material solidifies into a monocrystalline ingot on the seed crystal. The specified orientation of the monocrystalline can be seen exactly by means of the pulling ridges. In reality, the animated process shown here, speeded up, lasts between 1 and 3 days. Removal takes place with great care, because any improper handling of the ingot could damage the material. The finished monocrystalline ingot is then transported away for further processing. The silicone ingots made in crystal pulling need to be proportioned for further processing. This is done in a first step with inner diameter saws. According to an exactly defined sawing protocol, the machine cuts off the seed and tail cone and proportions the ingot into several pieces. Reference wafers are cut out of every ingot and transferred to quality inspection. In the next step, the cut ingot pieces are ground to a specified diameter. In addition, the crystal levels are defined using an X-ray goniometer and the later position for the flat and notch marked. Inside the flat and notch grinding machine, we set this marking with a video camera and start the grinding process. A notch or flat, a larger, even surface, is needed. Our customers use the notch and flat for setting and alignment purposes. Worldwide, the majority of wafers are processed by inner diameter sawing machines. The saw blade consists of a chrome-nickel steel sheet with a diamond coating and is approximately 0.3 millimeters thick. At inner diameter sawing, we permanently control the saw blade alignment and adjust it through the ingot feed. The subsequent cleaning of the silicone wafers takes place in an ultrasonic bath. Multi-wire sawing is another very effective sawing process. Suspended from a machine adapter, the silicone ingot is installed in the wire saw. During the slicing process, a wire with a thickness of 0.18 millimeters runs at a speed of 10 meters per second over the rollers. Adding slurry, the ingot is lowered down into the web of running wires and cut into slices. Grinding the untreated edges of the sliced and ground silicone wafers in edge grinding machines applies profiles to them. This generates a predefined edge profile, thus reducing the risk of breakouts during further processing. The profile shapes are generated according to our customer's specifications. At laser marking, we apply, according to our customer's wishes, either an OCR or barcode sequence to the wafer. This allows us to backtrack the history of the wafer in production. We inspect the mark and the mark dimension under the microscope. Lapping improves the surface parameters of the silicone wafers, removes the remaining inhomogeneities, and generates a smooth surface texture. We lap the wafers between two contra-rotating lapping plates and with slurry. As a lapping grain, we use aluminum oxide or silicon carbide. A careful cleaning of wafers after the mechanical processes takes place in various bath sequences. The wafer carriers run through several rinse baths, where ultrasonic agitation and elevated temperature enhance the cleaning effect. In this process, any remaining contamination will be removed. While the cleaning process only removes the contamination from the surfaces, etching removes part of the silicone layer chemically. A caustic etch medium has an alkaline solution and a nitric hydrofluoric acid combination as an acidic etch produce a predefined, clean, and very smooth wafer surface. Etching also reduces the wafer thickness. Measuring the electrical resistivity of a wafer is negatively influenced by so-called thermal donors. These are oxygen-related inhomogeneities within the silicone crystal, which give off unwanted charge carriers. As a consequence, they distort the original parameters for conductivity and resistivity. A short heat treatment at above 600 degrees Celsius, followed by rapid cooling, eliminates these thermal donors. We call this process annealing or heat treatment. Gettering is a process by which metal contaminants can adhere to predetermined areas within or at the silicone. Intrinsic gettering is created in crucible pooled material. Oxygen precipitates form centers in the wafers at which metallic contaminants can adhere. Extrinsic gettering offers several methods such as wet blast damage or standard damage. With wet blast damage, we intentionally damage the wafer backside with a water quartz powder slurry. With standard damage, we use rollers to treat both sides with lapping powder. For extrinsic gettering, we apply a polysilicone layer onto our wafers. production of polysilicon layers takes place by way of decomposition of monosilane. At a temperature of about 650 degrees Celsius, the gas is distributed over the wafers within a quartz tube. Silane molecules arrive at the wafer surface and decompose, giving off hydrogen. This builds a silicone layer of up to 10,000 angstrom, which will bind contamination during the later processes at our customers' facilities. Contrary to poly deposition, which is used as a getter, LTO coating is used for back sealing, which is required by the subsequent epitaxy process. It prevents dopants from out-diffusing from the wafer backside and altering the dopant concentration within the epitaxial layer. The process gases monosilane and oxygen are directly applied onto the wafer. Each wafer is coated 4 times per run. This creates a highly homogeneous oxide layer. The thickness of LTO coatings ranges between 2,000 and 8,000 angstrom, which corresponds with a wavelength range of visible light. Before the wafers are mounted on the polishing carriers, they must be sorted by thickness. We call this process polishing pre-sorting. It guarantees that there are only small thickness deviations among the wafers on one carrier. Wax is spun onto the carrier plates and the silicone wafers are pressed onto it. The polishing process consists of several steps. Through rotation of the polishing plate and the carrier plate and the application of pressure and slurry, the final surfaces of the wafers are polished to a mirror finish, a so-called haze-free polished surface. Some of our customers require specific wafers with an even higher degree of surface perfection. Such wafers are mainly used for the production of microprocessor and memory devices. Epitaxy is used to deposit a thin monocrystalline silicone layer onto the polished front side of the wafer. The deposition takes place at a temperature of well over 1,100 degrees Celsius in an atmosphere of hydrogen, trichlorosilane, and dopant. The trichlorosilane decomposes at the hot silicone surface and is deposited at the wafer surface as an ultra-thin and perfect silicone layer with a thickness of only a few microns. Final cleaning removes the last remaining particles from the wafers. For this purpose, we use final cleaning automats with various process steps. In a spin dryer, the absolutely pure wafers are dried at 5,000 rotations per minute. After drying, an operator checks the wafers in a darkened room. Continually increasing quality requirements make packaging of wafers a crucial aspect. The quality of the final cleaned wafers must be maintained. The main packaging element is a sealed shipping box which will not give off particles onto the wafers and protects them from shocks. This box is additionally covered by a multi-layered plastic bag plus an aluminum bag. A low-pressure atmosphere is generated within the box. Each box carries a data label so the wafers can be traced back later if necessary. Thus protected, we ship Siltronic wafers to our customers throughout the world.